How do you know if your vias can handle the current through your PCB? I got this question from one of my mentees who was wondering, how do I get up to speed in electrical engineering design and fundamentals for PCB layout? And one of the questions was how much current is going through these boards. They had a 26 layer PCB, and there was some discrepancy between senior engineers on how many vias you needed. So this may sound familiar if you've been through this. How many vias do you need? How much current can they put through the PCB? Well, I know you may not want to hear it depends, but it depends. There are equations to calculate this or to estimate it, but you're going to end up needing to use a spreadsheet, doing hand calculations. It's easier just to simulate. How do you do that? Well, first let's understand how current behaves and why it becomes more dense in certain areas than others. Every via on your PCB uh, and every copper trace, copper pore carries electrons that are moving over time. So it's current. When the density of the current, meaning the density of the electrons in a specific area of the copper, is too high, let's say in a via or a narrow section of your PCB, the voltage on there is going to drop. We call this IR drop. So while the rule or best practice rather is to make your traces as wide as possible, place as many vias as possible, and hopefully it goes well, you're crossing your fingers and hoping for that to work. Instead, what you really need to do is, unfortunately, or maybe fortunately, go into simulation. So let me show you how that goes into the workflow. What I like to do is go into my board in Allegro X, right? And then go into the Analyze Workflow Manager. Here, I have options in Sigrity X Aurora on the back end to analyze my IR drop across my design. I set up a bunch of voltage regulation modules like these right here, and I made sure to select specific components to be my VRMs. Let's say I have J13 as a VRM, or voltage regulation module, because it's a connector, and my chips would serve as sinks. Matter of fact, I can look for more J's here. Those are selected and whatnot. So with all of those being selected, I would hit apply, then OK, then run an analysis. Oh, also setting up my sinks. So what is pulling current, using current across the PCB? I only selected some connectors to be my voltage sources, with chips being my voltage sinks. I think I'll include U29 as well in this list, and also U2. So we'll hit apply, then OK. For my analysis options, I'll go with the default. I do have the option to translate the antipad as void, do some topology extraction for the layout, but I'm going to leave everything with the default. What's really cool is that since I have multiple processors on my chip, on my computer, then I can enable distributed computing to process everything across multiple cores of my CPU. So then we're going to run or start an analysis on the IR drop of the PCB. We'll let that run, and there we go. It is finished. So let's quickly jump to, let's say, the top layer of the PCB, view IR drop visions, and now we can look at the IR drop table to see where's the current flowing, how much current is going through there, and even the voltage, like the differential in voltage as well. So if the differential in voltage is getting too low, that gives you a clue of where current might be a little bit more dense. If I enable log scale, this gives me a better scale for what I'm looking for. I notice, hey, the voltage differential is in the 44 millivolt range. What's going on here? So that brings that to my attention. I'll ask maybe what's going on with the current density. This color map shows where the current density is the highest. Red regions indicate high current density, meaning there's more voltage drops, and so or vice versa, like when I showed you the IR drop. Here are some clusters here. There's also another cluster here, like this via and this trace seem to possibly have an issue. But what's great about the table is I can look specifically at vias. So this via, okay, this fails my current density pass-fail test. Let's see what else. This one also fails here. And these criteria are just based on what you set for your design. Okay. Here, there aren't enough vias, or there's too much current density happening with this one via. So I may need more vias to distribute that current more. Let me show you the vectors. So if I choose show vectors, we see also the current flow. Notice how really what's happening is that the electromagnetic field, let me explain this. What's really happening is that the copper structures in this PCB are done in such a way that the electromagnetic field has been allowed to spread where we may not want it to in a suboptimal ways. So with the electromagnetic field spreading as a wave, it bumps electrons around in the copper structures. Those electrons being bumped around at significantly slower speeds, by the way, but just being agitated thousands to millions to billions of times per second, they start to drift and flow in different directions. So the field is really doing this, and it's causing the electrons to move. Then what we see here is these electrons are flowing and drifting in these areas. They get choked more so around this area and this area with the red and orange fields. There are fewer electrons in the green and bluish areas. So we could see how the electrons are flowing. And then as far as how dense they are, these are our like choke points here. You may want to add more vias as needed, even on the plane. You may actually want to add more grounding vias as well to more efficiently get energy through the dielectric and distribute those currents and the electrons appropriately. Yeah, these areas right here are forcing the electrons through, like narrow areas. They're forcing the electrons through them, and that becomes a problem. Little bottlenecks here. Also happens, let's say you have many vias but insufficient power planes. So what that means is just because you place more vias doesn't necessarily mean that your current density is going to be suitable for that area. What that ends up looking like is your board goes out in the field, it's used for say 6 months, 12 months, and then it starts having, people report that there are some heating issues, some problems with the temperature, and then your thermal cycling starts to happen or more frequently than you would expect, and then you have to do like a quick recall and test things out. Okay, so that's why this is very useful. It saves you a lot of trouble in the future. The ways to solve this problem, how do we solve and fix this? Well, you can again add more vias in your higher current density regions. So that's a solution. And by vias, I'm specifically talking about oftentimes not just your core current via, but you want a via for your signal or power and a ground return nearby. See what we've got going on here? Because of that, we have the electromagnetic field having its signal and then also a return region or adjacent return set of vias to push that signal through the PCB dielectric. So here, let's say we've got DDR3 underscore A1, right? And it has a ground reference that it refers to, power or what have you. We're going to want that. We're going to want an adjacent via somewhere nearby or a copper structure like ground pour right underneath it as well. That can count to have the signal coming out of that via, the electromagnetic field specifically, have something immediately coupled to be its return reference. That way the field remains contained and stays right underneath this track. If you haven't seen my video on how to do return path simulation, you may want to check that out or attend any of my discussions or lessons, like in a webinar. Okay. So another solution for the current density problem is having wider plane connections. You see how we have ground all over this entire PCB? Well, if you have power, okay, if you have power nets, you're going to want to make those as wide as possible. So we see our shapes here, our power net shapes, that when I move my mouse cursor over, they're highlighted and they provide enough distribution for those electrons to flow. That's another way. So wider plane connections. You can also reposition your components to shorten the current path. Okay. If you want to reduce IR drop, maybe bring your components closer to each other where there is a problem. So if you have like a major drop in voltage, you may want to look at and say, hey, looks like between this chip or this connector and the other connector, there is a large drop. Is there any way we can shorten this trace so that it doesn't have to go as far and we don't have as big a drop? Okay, that's another way to fix this as well. So these are layout changes you can make to reduce the IR drop without changing the schematic at all. IR drop is a geometry problem with PCB layout. Sigrity X Aurora shows you exactly where the current flows and where it struggles. If you fix the geometry, you will fix your voltage delivery by way of your current density. So this is how you can find out how much current is going through your vias through simulating with tools like these. Thanks very much for watching. Get this into your workflow if you find this helpful. Leave comments, and I'll see you in the next video.